Problem A2. A student designs a simple integrated circuit device that has two inputs, VA and VB, and two outputs, VO and VG. The inputs are effectively connected internally to a single resistor with a effectively infinite resistance. The outputs are effectively connected internally to a perfect source of EMF E. The integrated circuit is configured so that E equal G multiplied by VA minus VB, where G is a very large number, somewhere between 10 power 7 and 10 power 9. The circuits below are chosen so that the precise value of G is unimportant. On the left is an integral schematic for the device. On the right is the symbol that is used in circuit diagrams. Question A. Consider the following circuit. R1 equal 8.2 kilo ohm and R2 equal 560 ohm. Are two resistors. Terminal G and the negative side of V in are connected to ground, so both are at a potential of 0 volts. Determine the ratio V out to V in. Solution for question A. The key idea is that E is finite. Then VA approximately equal VB since G is so large. If we work exactly, then the answers will contain terms like VB minus VA over G, which are negligible. Thus, we can find the same answers by just setting VA equal VB. For part A, we will not assume that VA equal VB. Since terminal G is grounded, we have VG equal 0 and VA equal V in. So, V out equal G multiplied by V in minus VB. No current runs between A and B, so any current through R1 also flows through R2. Then ohm laws give us equation VB over R2 equal V out over R1 plus R2, which will give us this relation between V out and V in. We just need to express V out through V in. That will be this expression. But 1 over G is very small compared to this part. It means that V out over V in approximately equal this relation, or 15.6. That was the answer for question A. Question B. Consider the following circuit. All four resistors have identical resistance R. Determine V out in terms of any or all of V1, V2 and R. Solution for question B. For this part we will assume that VA equal VB, and again VG equals 0. It's grounded. And if current I flows through the bottom resistor below B and G terminal, this one, then V2 equal to VB. Since the voltage drop across the bottom two resistors must be equal. Similarly, the voltage drop across the top two resistors is equal. So it means that V1 plus V out equal to VA. Then V out equal to VA minus V1 or V2 minus V1. This was the answer for question B, and this circuit is a subtractor. Question C. Consider the following circuit. The circuit has a capacitor C and a resistor R with a time constant RC equal tau. The source on the left provides variable but bounded voltage. Assume Vin is a function of time. Determine Vout as a function of Vin and any or all of the time t and tau. Solution for question C. We again set Va equal Vb equal 0. Then the capacitor charge and the current satisfy these two equations. Q equals C Vin and dq over dt equal negative Vout over R, where the second result follows from Ohm's law. Then we have Vout over R equal negative C dVin over dt, and finally we have Vout equal negative tau multiplied by dVin over dt. This was a solution for question C, and this circuit is a differentiator. That were 3 answers for question A, B, and C of problem A2.